And next up, we have Srujana Subramanya from USC, and she's presenting on galaxy morphology classification.
Hi, everybody. My name is Srujana Subramanya. So I will be presenting about the galaxy morphology classification workflow that I've been working here at the SciTech lab. So I've been with the SciTech lab from July, and I work here as a student worker. At USC, I'm pursuing master's in electrical engineering, and my areas of interest is basically deep learning, computer vision, and image processing. So the workflow, the contents, and the way that this presentation is going to go on is going to be in this order. So I'm going to talk about the overview and the overview of the workflow, the different classification categories that I'm targeting in the workflow, and a detailed walkthrough of the entire workflow and how it is being executed with Pegasus, the data set, pre-processing and data augmentation involved, HyperParameter Optimization, the model and architecture chosen, and finally about the evaluation. So yeah, so regarding the overview, why this task and why did we choose to do galaxy morphology classification to begin with? So the different shape, form, structure of galaxies basically tells you how a galaxy came into existence, how it was created in the first place. So it kind of becomes really important to understand how galaxies evolved and how they formed. So I think keeping that in mind, classification becomes one important task. And according to this recent survey called the Sloan Digital Sky Survey, it resulted in tremendous amount of images of galaxy images, and asking an astronomer to classify these images into different categories, it's nearly impossible for him to classify thousands of images. So it becomes of paramount importance to kind of have a machine do it for you and do it in a very quicker way. So that's why this project, and there's a paper written with and which is being followed in this entire workflow. So those images are an example of how galaxy images look like. So what are these different morphologies that we're targeting? What are the different categories that the paper aims to look at? So these are the 5 categories, or the 5 classification categories that the paper aims. So first one is it's completely round, and there's in between smooth, that is it's in between completely round and the cigar shaped. And then you have the third one, the cigar shape, the fourth one, edge on, and finally you have the spiral. And to get an idea of how exactly each of these categories look like, I have an image put up. So from top to bottom, each of the rows represent the different categories that I just spoke about in the same order. And for our workflow, each of these categories will be referred to as 0, 1, 2, 3, and 4. So that's how the workflow is going to go about. This is the detailed walkthrough of the workflow. So how exactly data is being captured, and how I'm implementing the huge monolithic script, breaking down them into jobs and executing them with Pegasus. This picture gives you an idea. So at first you have the data acquisition stage. So you kind of download the data and you save all of it into the current working directory or to some working directory. Then once you have the data, one important task with this particular workflow is that we need to obtain clean data. So originally when you acquire data, there's like 61,000 images, but for this workflow, you need about 29,000 images, about which I'm going to talk a little later why we need to reduce it. So once you obtain clean data from the larger data set, we go on to grouping data into a train, val, and test. And once you've grouped them into 3 categories, I have the data pre-processing jobs. So since you have a lot of data coming in, Pegasus really helps us speed up the process here. So each pre-processing job can be run in parallel, and all the images can be pre-processed at the same time. And one advantage with Pegasus is that, and the different pre-processing and data augmentation techniques followed is will be discussed further, but it involves cropping, downscaling, image rotation, flip, and adding brightness, contrast, saturation, and hue, and finally whitening the image. So these are the different pre-processing and data augmentation techniques followed. So once you have your pre-processing and data augmentation done, I target on having having to choose the best hyperparameters for the model. So the model or the architecture chosen for this is the ResNet. So you train the ResNet, and then I use the Optuna for Keras parameter optimization technique to kind of figure out which activation function and which optimizer suits the best for this job. And then I train the model, obtain the file, train model, and then kind of test it on the test data set, or just see how the different evaluation metrics that are of interest. Wendy? Thank you. So the data set. So the data set that I've used originally is drawn from the Kaggle Galaxy Challenge. So this particular Galaxy Challenge has 61,578 images. Each are of the dimensions of 424 cross 424 into 3. So they're all colored images. And this paper that I'm kind of implementing, however, uses only a fraction of these images. So how do you obtain these clean samples from a larger amount of images is using these rules, basically. So the data set also comes with like a CSV file telling you the different morphologically sound classifications for each image. So using those values, you kind of group them up and you get the smaller subset of the larger data set. So once you've obtained the data, you proceed on for the data augmentation technique that you talked about. So data augmentation is obviously going to be performed mostly on the training data set, and this is done in order to obtain or increase the data set by a factor of say 300 or 400. So that's the main objective of this pre-processing and data augmentation technique. So first you proceed on with image cropping. So you apply the scale jittering technique and you kind of range it between 170 and 240 with the training set and with every image. Once you've done that, we proceed on to resize the images and perform random cropping to obtain and to increase the size of the data set by a factor of 256. And then we proceed on to do rotation, and then you again increase the size of the data set by a factor of 4, and then you perform flip. So again, you have two kinds of flip. So you increase the data set by a factor of 2. And finally, applying brightness, contrast, hue, and saturation also is one of the pre-processing techniques that has provided good results in this workflow. So regarding the hyperparameter optimization, basically the entire workflow is written in the Keras framework. And for the pre-processing step, I've used a lot of scikit-learn functions. And for the hyperparameter optimization, I've used Optuna for Keras, the OPT Keras optimizer. And I found the best performing activation function and optimization function for the model. While doing so, I also implemented the Pegasus checkpointing technique, where I save the best performing hyperparameters after each epoch or each step in the workflow. So the model or the architecture chosen is the ResNet model. So why ResNet and why not anything else is going to be talked about here. So it's observed that the deep convolutional neural networks are one of the most chosen approaches in image classification techniques. And However, these deep convolutional neural networks are very difficult to train because of how many parameters they have. So they have like millions of parameters. So in such situations, ResNet, comes into picture where these residual networks that are involved in ResNets kind of ease the training part of neural networks. They have skip connections that kind of help they kind of help you to skip different layers and perform identity mapping to obtain the same results, but by performing training on fewer parameters. And this particular paper uses a modified version of the ResNet V2 model, which is shown in the diagram on the right. So this model is different from the ResNet V2 model because the only thing that they're doing is kind of giving, they're adding the parameter K as a widening factor, which kind of suits especially for galaxy images, which is why the ResNet architecture is chosen in this workflow. So once you have trained the model, you need to evaluate and see how you're gonna test it. The different evaluation metrics of target are accuracy, precision, recall, F1 score or F1 value, and confusion matrix. I've implemented this entire workflow on a smaller subset, and it still needs to be trained on a larger data set and seen how it performs. But that work is still in progress, which is why I don't have results for you. But this kind of gives a gist about how galaxy morphology classification is done and implemented in using Pegasus. So I think that's it. Thank you so much. And I also would like to thank Ryan, Patricia, and Eva for, giving me an opportunity and mentoring me while I worked here at SciTech Lab. Thank you so much.
Thank you so much. That's very, very great report. Any questions for Srujana?
Yes, I have one, Wendy. Thanks, Srujana, for your great talk. I had a question. So you said you tested on like a small data set and then you will move to the big data set.
Mm-hmm.
So how do you expect the workflow to scale? Like if it, takes a small time on a small data set, do you think it will take like a huge time on a bigger data set, or you can like easily add images and thanks to workflows target bigger and bigger data set if you wish?
So the training part of it is obviously going to take a lot more time than training on a smaller data set, but to add more images to the data set itself should not be a major task because like the process of adding a larger data set and training it, that part is easy, but to actually train it on a larger data set, it will consume a little more time. Because when I started off working with this workflow, I used as little as 10 images. So that is kind of during the building process where you kind of do that to get the model to work. And then I need to train it on like, say, 29,000 images. So the training part of it is definitely going to take time, but with the help of Pegasus, at least the pre-processing and data augmentation techniques can be implemented using parallel pre-processing, and that part might speed up.